In the last unit, we learned about using the normal distribution. However, the normal distribution, most of our examples there, we were dealing with situations where we asked, how likely is a certain observation of just usually one individual that came from that normal or potentially came from that normal distribution? So a good example of this might be if we were looking at butterflies, for example, and usually these things are maybe 82 millimeters in width, but we get one butterfly that's 86, and we want to know how likely that is. That's the sort of question we were asking in the previous video. So what we're going to do today is we're going to look at sampling distributions because we rarely work with samples of just one. Usually we have large samples, like if we were studying these Gulf fritillaries, we might go out and collect about, 16 of them and see what their average wingspan is. Okay, so just to sort of drive this point home, let me just sort of model the situation that I was just talking about. So let's say that based on years and years of data, we know that Gulf fritillaries have a wingspan of 82 millimeters with a standard deviation of 8. Now, let's say you go out and collect one butterfly that has a wingspan of 86. How likely is that to happen? Well, using the normal distribution, we could easily model this. This is very similar to the questions we had done before. So we'll put in 82, and we'll put our standard deviation in here of 8. Okay. And we want to know, well, how likely is 86 or more, for example? As you can see, that's pretty likely. And if you want to deal with this as in, how likely are we to get an extreme example of a butterfly? Because remember what this is. This normal distribution here, this is a model of the entire butterfly population. So all the Gulf fritillaries that have ever existed. So, 30% of the time we're likely to get specimens that are bigger than, or 86 millimeters or bigger. You see what I mean? So if we are sort of looking at that as, well, how likely are we to get really unusual butterflies, like either big ones or small ones, we could look at this at the other end. And so let's see, that's 4 above, so we would need 4 below. So we would need sort of outside of, I guess, what is it, 78 and 86, right? Okay. And then you see that's also quite likely. So it's pretty, assuming that nothing is going on in the Gulf fritillary population, it's actually fairly likely that from time to time we would get single butterflies that are either, bigger than 86 millimeters or smaller than 78 millimeters. There's about 62% chance of that. So that's pretty likely. So what we're asking, though, with the sampling distribution is a different question. So for this question, what we're going to ask is, what if we go out and collect 16 of these guys? Now, from our sample of 16, we could calculate a mean and a standard deviation. So what if we go out and we get 16? Now we're expecting the mean to be 82, right? Because that's what these butterflies normally are. But instead we get this really or seemingly high number. Now we know that just getting a single butterfly with 86 millimeters is pretty unlikely, but how likely is it that in a big sample of 16, the average would be 86? That's what a sampling distribution is used for. Now, solving a question like this is really, really easy. I mean, you still use a normal distribution, but we have to change things a little bit because we're working with a sample. So we need to know how the sample size is affecting the shape of the normal distribution. Okay, so let's take a look at this graph for a minute. All right. What this graph shows is it shows the effect of taking different sample sizes. So you see this really wide normal distribution here. Just ignore the labels here, but see this really wide normal distribution? That is similar to what might be going on in butterflies. So it's a distribution of individual scores. Now, what we have superimposed on that, you see this relationship, you can see that's a bit narrower. That's what that is. Those are means that have been generated by taking 4 samples at random from the normal distribution and calculating a mean. So, you know, if you take 4, let's just think about this for a minute. So if we just took 4 from this real wide distribution, yeah, we might get one over here, but we're more likely to get some in the middle. So if we then compute an average, the average is definitely going to be in here in the middle, and that's why it's narrower. Now, if you take even more samples, like instead of just taking 4 samples, you took 8, then you get an even narrower one there. So what's going on here? Well, one thing we can see is that as we take large and larger sample sizes and generate distributions of means instead of distributions of individuals, the standard deviation of those things is decreasing. Now, those standard deviations there, what they are, they're called the standard error. So if you have a single, a distribution of single butterflies, like a normal distribution of butterflies with n minus 1, n equals 1, that's just called standard deviation. But as soon as you start graphing, normal distributions of means, then these things are called sampling distributions of means, and their standard deviation is called the standard error. Now, calculating the standard error is really easy. It's just the standard deviation divided by the square root of n. And that's kind of what you can see going on here. See, when the denominator here is increasing, it causes this value to go down. So that's why these are getting narrower. As you increase the number of samples, the standard deviations of each one of these normal distributions gets narrower. So again, the main point is this real wide one, that might be like, the distribution of all the Gulf fritillaries out there. This one that's a little narrower here, what that is, that's a distribution of means. So you go out, you collect 4 of these fritillaries, you calculate a mean. That's a data point. You go out, you collect 4 fritillaries, you calculate a mean. That's another data point. If you then graph all those means, this is the curve you get. So narrower than the one based on individual butterflies. And then this one at the top is even narrower because it's a graph of means of size 8. So these two things, again, what they're called sampling distributions of the mean. Whereas this other distribution here, that's just a plain old normal distribution like we did in the last unit. Okay, so this little relationship here is what we need to solve the question of the fritillaries. So what I'm going to do is get back out of this, and let's go back to that question and see what we would do with it. All right, so what we have is we have n equals 16, right? So the square root of that is 4. All right, now which of these two standard deviations are we supposed to use? Well, we should be using that one because that is the population standard deviation. This is just a sample standard deviation, which is an estimate of that. Okay. All right, so again, let's kind of go back and take a look at what we were doing here. So here, what we were doing, we were trying to figure out how likely is it that a single butterfly would be 86 millimeters, or on the other side, 78 millimeters wide. But if you are dealing with a sampling distribution with n equals 16, then that's going to reduce this. So remember let's look at the formula here. Actually, I think it may be easier to look at it this way. All right, let me see here. Okay, here it is. All right. So this is how we would solve that. All right. So first of all, the mean of the population is actually equal to the mean of the sampling distribution. So if the butterflies in the population have an average wingspan of 82 millimeters, then if we take samples of this, no matter how many or how big our samples are, the mean of every one of those distributions is going to be 82 millimeters. Okay. Then the other thing we saw is that as these sample sizes get bigger, right, they decrease, or the standard deviation decreases. So this is the symbol that Lane uses for standard error. So the standard error will be equal to the population standard deviation divided by the square root of the sample size. Okay. All right, so the standard deviation of the sampling distribution, this is referred to as the standard error of the mean. All right, now let's go back to our fertility example. So applying this to the fertility example, remember we had 82 plus or minus 8 millimeters in the population. So if we take samples of size n, then the mean of that distribution is going to be 82, but the standard error is going to decrease down to 2. So it would be 8 divided by the square root of 16. So now we can go back and model this. All right, I'm just going to start this one over again. So just so we can do it from the beginning. So we'll kind of go back and forth between a couple here to erase it. All right, so again, what we're generating here is we're going to model sampling distributions of the mean of these Gulf fritillaries. So if we were just looking at the population, of the Gulf fritillaries, this is what the population normal distribution looks like. All right. But if we go out and we collect samples of 16 and generate means over and over and over again, look what happens. Then the standard deviation drops down to 2. Did you see how all these numbers got closer together here? Okay, so it's much narrower. So the standard deviation is now only 2. Okay. All right, so where does a mean of 86 fall on that? So if we were just looking at greater than 86, as you can see, that's now really unlikely. And then you could imagine, if we doubled that, so we could do the same thing we did before, 78 and 86, just to figure out, what about if we were asking how extreme it is? It's still really unlikely. So this is one of those scenarios where the chance of getting a mean of 86, if you have 16 butterflies, is pretty unlikely. It's really unlikely that would happen. And so usually what people would do is they would conclude, well, something seems to be going on with the fritillaries this year. Maybe it was a year when it rained a whole lot. Okay. All right. So here's kind of the results of what we got there. All right. How likely is this observed mean of 86 or more to occur? Well, just looking at the one end, we saw the probability of getting 86 or more, and this is the type of questions you're going to get in Lane's book, are going to be 0.023. So quite unlikely for that to occur. So what that means is something's going on. Scientists would conclude that these fritillaries did not come from this population. So either the butterflies have changed because of lots of rain, or maybe somebody collected them in another country. Because this is very unlikely to occur, Most scientists would say that no, those Gulf fertilities are bigger than the population. All right. Um, Frequently, we want to know the differences between means. So, a lot of times in science, we have control and experimental groups, and we generate two means from samples that we take. And so we need to know, well, how do we deal with a situation like that? So from this point on, we're going to look at sort of some special situations where we apply, where we work with sampling distributions. Okay. All right. So this is what we had before, the variance of the variance of the sampling distribution of the mean is equal to, right, the standard error is equal to the standard deviation divided by the square root of n. We can square all that and get the variance, right? Okay. Now, from the variance sum law, this is something that's introduced in this previous chapter. You may remember that if we add or subtract a bunch of means, like for example, if we wanted to know the difference between a control group and an experimental group, the new variance is equal to the sum of the other variances. So you can kind of show that the sampling distribution or the standard error or the variance of the sampling distribution is equal to the sum of the individual standard error, I'm sorry, variances. Okay, now here's an example. So what if we were looking at corn, for example, and we're going to try out this, this new fertilizer? Okay, so we've already got some information from the population. So we've been using this fertilizer for years and years and years, and we have these parameters. So the certain strain of corn grows to 110 plus or minus 8 centimeters with the fertilizer, and 105 plus or minus 10 centimeters without the fertilizer. So we're going to say that these are parameters. And we're going to test a new batch of the fertilizer to see if it works as well as the ones we've used before. Okay. So we plant two fields, one with fertilizer and one without. And from each of the fields, we're going to go out and we're going to collect 10 plants and take measures of them. So we do that. But whoa, what's going on? For some reason, this year, the fertilizer, maybe it's not working. That's what we want to know. Or maybe somebody switched out the fertilizer with distilled water. I don't know. But for whatever reason, the fertilized plants are actually shorter than the fertilized ones, and we're expecting just the opposite to occur. The question is, how likely is this given these parameters in the population and given that we have a sample size of 10? Okay, well, what do you do? All right, well, let's first of all recognize this as a difference between means. Because what we're going to be working with is we have a group of fertilized plants and a group of plants that aren't fertilized. We calculate two means, we compare them, and the means are 1 centimeter apart from one another. Okay? So, using that variance sum law that I was just talking about, the variance would, of this, the sampling distribution, would be the sum of the individual variances. Okay, so in other words, you can sort of think of this as kind of the remember the standard error of the difference between means is going to be the square root of that. All right. So what we would do is we would take our our two variances. So for the fertilized group, we have 100. Okay, so 10 squared. And then for the, no, I'm sorry, that's the unfertilized group. Unfertilized group is standard deviation of 10, so we'd square that, divide by the sample size. All right, and then we have the other group, so we'd square that, that's 64, divided by the sample size. So that gives us 16.4. All right, that's the variance of the sampling distribution of the means. And then here we have the standard error, which is the square root of that. Okay. All right. So what we are going to generate then is we're going to generate a distribution or a model of the difference between the means. So normally what happens, in other words, this is the model we're going to generate. We're going to generate what happens when you have fertilized, non-fertilized plants subtracted from fertilized plants, these means. So the difference between the two means is 5. You see that? That's the difference between the two population means. Okay. But we have a sample, a certain year we have, so these are parameters, see that? And we have samples, so this time we're going to let 1 be the fertilized group and 2 be the non-fertilized group. So when we subtract these, we get -1, and we're expecting +5. Okay, so how likely is that? Well, we can model this thing, all right? So actually, I'm going to, yeah, I'll just use that. I think that should be fine. Let's model this. So what I'm going to model here, I'm going to model the difference between the two groups. So normally, when we subtract unfertilized plants from fertilized plants, the fertilized plants are 5 centimeters taller. So this is what normally happens, okay? Now, what is the standard deviation? So this, since we're working with a sampling distribution, what we need for the standard deviation is this value that we calculated here. So I'm just going to copy that. I did that with a calculator earlier. I think y'all can probably handle that part of it. So we're going to put that in here. Okay. All right, so as you can see, with that much variation, there are times when we get values a little below 0, I guess. So what we said is this year they're 1 centimeter shorter when we're expecting it to be a positive value. So if we wanted to look at that end of the distribution, how likely is it that we would get a value 1 centimeter shorter? Well, there's about a 7% chance of that. Okay. All right. So what do we conclude based on this? All right. So using the normal calculator, you get a probability of this occurring about 0.069. So this is low, but it's not really as low as the 5% cutoff that's usually used. So most people would say, well, it could have happened by chance, maybe not. I mean, maybe the fertilizer really isn't working, but this evidence isn't strong enough for me to definitely say that the fertilizer doesn't work. And then if we looked at, the two-tailed, what we call the two-tailed probability, like both ends, how likely is it to get extreme values of -1 or at the other end would be 11, then it's essentially double that. Okay, so that's going to happen. So from time to time, even if, and that's what these graphs show us, even if the fertilizer is behaving like normal, okay, what we have in our graph here, this is the difference between fertilized plants and unfertilized plants. Even if it's behaving by normal, well, on average, with samples of 10 each, you're going to get means of 5. But sometimes, yeah, the plants are going to be a little smaller, and the control plants may even be a bit taller. That's what's going on over here. They're 1 centimeter taller in the control group or the unfertilized group. And then occasionally, we're also going to wind up with fertilized plants that are unusually large, like 11 or more. Okay? That's what this probability is telling us. Okay. All right, then. Well, we'll talk about the central limit theorem real quick here. So take a look at these graphs for a minute. This is actually just taken from Lane's book. So here you have a population. You see how it's like not normal at all. Well, look at this. If you take this is he has this little simulation thing that you can try out if you can get your computer to work. A lot of his simulations, I can't get them to work on my computer, but if you can get it to work, you can actually do stuff like this. So if you take, five samples from this and you calculate a mean and you do that over and over again, you actually get a distribution that is almost normal. I mean, this thing's a little platykurtic, so it deviates a little bit from normal. But then if you take 25 and you generate a sampling distribution of means, it really is just almost normal. So there's something called the central limit theorem that tells us that this kind of thing is going to happen. So what it says is the sampling distribution of any statistic will be normal or nearly normal as long as the sample size is large enough. So with this crazy distribution, sampling distributions of means are almost normal even when n is equal to 5. When you get to 25, they're really getting close to normal. I mean, they're only going to definitely be normal if the sample size is infinity. So, but usually you get pretty close to normal even with pretty small sample sizes. All right. There is an exception to this, and that is with the correlation coefficient. All right, so what we see here is a sampling distribution of a correlation coefficient. So here we have a correlation of 0.6, so that's a positive correlation. And this is the sampling distribution for n is equal to 12. As you can see, that is clearly skewed. Now here's the thing, if you start increasing n, or if you get r closer to 1, this gets even more skewed. So, nothing is going to eliminate the skew. So what do we do if we want to answer a question like we were doing with the Gulf Fritillary example that we saw a minute ago? Well, there's a distribution called Fisher's Z that can be used. All right. So there's something called Fisher's Z, which can be produced from correlation coefficients through a transformation. And Fisher's Z has a normal distribution. So even though Pearson's R, sampling distributions of Pearson's R are skewed, you can convert a number like this into a z-score, and those have a normal distribution. Okay, there's actually a formula for this, but don't use this formula. Instead, we're going to use a calculator in Lane's book to get z-scores. All right, well, that's kind of a lot to take in, so let me give you an example of when we might use this kind of thing. All right, so here's an example. So let's say at Broward College, height and weight are correlated, and we have a correlation coefficient of 0.8. So that's a pretty high correlation. So that's out in the population of the college. So we've got a class where in our sample, all right, so remember this is the population. We have a sample, we have 19 students, we'll say, in the class. And we get a correlation of 0.6. Oh, those are pretty different. So, kind of like we were doing with the Fritillaries, I want to know, well, how likely is this? Should we expect this value just by chance, or could something else be causing this lower correlation? What do we do? Well, remember, a sampling distribution of R is going to be skewed, so we can't work with that directly. This is what we do. What we do is we generate a normal distribution that models the population by converting R to Fisher's Z. All right, let me show you where that is. Okay, so here we have Lane's calculators. All right, and if you go down the list, there's this thing called R to Fisher's Z. Or I tell you what, let me show it to you on the home page also. So when you go to the calculators here, all right, see there's R to Z. Okay. So to get values, correlation coefficients on the Z distribution, you would put in 0.8, for example. Remember, that's what the parameter is. Wait, I did something wrong. I think I put in a comma instead of a period. Okay, there it is. Okay, so there's the parameter. So a correlation of 0.8 has a mean on Fisher's Z of 1.09. All right. Now then, we also had that sample. So in our class, so for example, this is what it is for the whole school. That's like the parameter. And then in just our sample, our class, we had 0.6. Okay. So as you can see, that's a little bit lower. All right. Now, Fisher's Z is a normal distribution. Okay. So let's see what we've got here. Okay, now those are here too. So now what we would do is we go to our calculators again. We open up the normal distribution. So Fisher's Z is a normal distribution just like this. And we would put in that mean that we just got. All right. I had that written down over here. 1.099. Okay. 1.099. All right. And what we're interested in is how likely of scores that are 0.693. So that's the z-score that corresponds to a correlation coefficient of 0.6. Okay, so this is the kind of thing we're trying to find. Now, what we haven't done anything yet with is this standard deviation, so I need to tell you how you get that. All right, so remember the standard deviation of a sampling distribution is called the standard error, right? So in the z distribution, it's 1 over the square root of n minus 3. This is nice. There's no standard deviation in there, right? But that's the standard error of the z distribution. So in the case of our class, we said our class had 19 people. So that would be 19 minus 3 is 16. So 1 over square root of 16 is 0.25. Okay, so let's go back to our model here. Okay, now we got it. All right, so what we've done is we've taken the population of Broward College, so we can't generate a sampling distribution for correlation coefficients directly. So what we do is we take the correlation for Broward College, which is 0.8, and we put it on a z distribution, which is that. This is called a transformation. So it's like we transform the correlation coefficient to a z-score. And there it is, the mean. All right. Now then we had our class. We had 19 people in the class, so it's kind of like we figured out how much everybody weighed and how tall they are. And then we generate a correlation coefficient from that, and we get 0.6, which is lower. Where does it, how likely is that to occur just by chance, assuming that we're part of Broward College, which we are, okay? Or is something weird going on in our class? Well, again, you won't find 0.6 on here, so you have to convert it to a z-score. We found that that was 0.693, which would be right there. So the probability of getting a correlation 0.693 or lower, all right, would be about 0.0522. Now, if you wanted to look at both ends, like if you wanted to ask the question, well, how likely is it that we would get such an extreme correlation, we could essentially double that, all right? So as you can see, that's actually a little bit above the usual 5% cutoff for hypothesis testing. And once you double it, it's definitely above that. So we'd probably say, oh, yeah, we've got a low correlation coefficient in our class, but maybe it's not that low. I mean, it could just happen by chance. I'm not ready to say that, people are unusually heavier in class or something like that. Okay? All right. All right. right, so this is essentially the procedure that you would follow when you're trying to solve questions, kind of like the fertility example, but working with the z distribution. All right. Okay, now there's one other scenario that can be a little tricky to work with, and that involves proportions. So take a look at this question. So let's say, based on years of data, here in Davie, we could say that the Gulf fertilities are like 10% of the butterflies. Okay. Well, I go out this year, we've had kind of a dry year. I go out and I collect butterflies, and, I collect like 50 of these butterflies. Um, and in my sample, it's 16%. How likely is this? So you're looking at this is kind of similar to what we've been doing. We kind of have a sample, right? 50. We have a parameter, all right? And then we have like a sample statistic. We're kind of asking how likely is this sample statistic given this parameter and this sample size. So you're kind of looking at this, and I hope you're thinking, well, that looks like a sampling distribution question. It's very similar to the ones we've seen before. But it's not. It is a binomial problem. So this is one of those situations where you got to be kind of careful what you're doing. As you're going to see, there's a way to do this by making like a normal distribution, kind of like we've done with the other examples. But you should recognize this as a binomial problem. And so this is what it would be. If I collected 50 butterflies, 16% of 50 butterflies is 8. That's where that 16 came from. That means out of my 50 butterflies, 8 of them are Gulf fritillaries. Hopefully now it's looking like a binomial problem to you. So we have a fixed rate of success. We're expecting 10%. We have 50. So we're kind of expecting 5 to be fritillaries. But instead we had 8. How likely is 8 or more? That's a binomial problem. So you should know how to do that already from previous sections. Okay, all right, so here's the kind of question. So we'd use a binomial distribution for n equals 50, pi equals 0.1, and you could ask questions like, what's the probability of 8? What's the probability of 8 or more? Or we could look at the extremes. What's the probability of 8 or more, or 3 or less, or something like that, okay? All right, but there's a way to do this with a sampling distribution. Nonetheless, the problem can also be solved with a sampling distribution of the proportion, where the standard error of the proportion is equal to the square root of pi times 1 minus pi over n. All right, all that's underneath the square root sign. Okay, so this is similar to what we were doing with R. So you can kind of generate a normal distribution with that standard error, and then you can actually put these things on it. So that would be the mean. This would be this extreme value you're looking at. This would be the standard error of that distribution. All right, so let's see how we would do that for this one. So and the mean of our sampling distribution is going to be the same as the population mean. So 0.1. So, right, 10%. And we have a sample size of n equals 50. All right, well, what's the standard error then? So the standard error of the proportion, because this is a proportion, would be pi times 1 minus pi over n. So it would be 0.1 times 0.9 divided by 50. There's the value. Okay. What we want is the probability of 0.16 or more with this standard deviation and population. All right, so let's see if we can do that real quick. I'm just going to copy that so I don't make a rounding error here. All right. So here we have a normal distribution. All right, so what this is this is the Gulf fritillary population. So normally, it has a mean of 0.1. So even in a sample of 50 butterflies, we're expecting 10% of them to be fritillaries. Now we need to enter the standard deviation. All right, so that's the one I calculated using that formula. Pi times 1 minus pi divided by n, and then you got to take the square root of that whole thing, and that's how you get this. All right, so what we have is we have a proportion that's over here somewhere. So above, all right, 0.16. All right, what is it? Recalculate. All right, well, there it is. It's about 8%. All right, so 0.078. Okay, we can kind of jot that down. Now, what I'm going to do is I am going to actually work this using the binomial method and see how it compares to that. All right, so let's try the binomial approach now. All right, so if we had worked this as a binomial problem, right? So what we have is we have 50 butterflies, all right? The average rate of success, 0.1, okay? And what we got is we have 16, no, let's see, what did we get? It was 8, yeah, 8 or more, right? So we want above 7. All right, okay. As you can see, this is not exactly normal. And notice that it's pretty far off. What happened? Well, do you remember the rule of thumb that we used in the previous unit? So we said that the binomial or a normal approximation of a binomial distribution will work when n times pi is greater than 10 and n times 1 minus pi is greater than 10. Well, here, pi is 0.1, and 0.1 times 50 is 5, which is less than 10. And that's why this score is so far off. Now, if it had been a little closer, like if we were dealing with 0.5 or 50% were Gulf fritillaries, we probably could use this approach safely. All right, so let's see here. All right, so this is kind of what we did. So there's the probability we got by using this sort of normal approximation method. Now, if we actually, then we tried to do this using the binomial approach, and you get, 0.12. So the sampling distribution was off somewhat. Okay, so it would have been better, and this is why you use the binomial distribution, and that would have been a better experimental design for this particular study. Okay. Now you could try this with n is equal to 100 just to see if things are different. So instead of, just sort of adjust all those numbers, instead of there being, a sample size of n, what if you had a sample size of 100? Then using both approaches, and I'll let you try this out on your own, you should get probabilities about 0.02. And this time it works because 100 times 0.1 is equal to 10, which is pretty close to 10, so it's usually fine. All right. Okay, and with that, we will end this presentation on sampling distributions.